Good afternoon, everyone, and welcome you all to our webinar series. I'm your host, Surathep Kyoham from Chulalongkorn University, Thailand. I'm glad to see you again in our webinar series. Today, we run two talks at 3 p.m. and 4 p.m. Now you're on the first session at 3 p.m. Once we finish this session, you can later join the other session. And one of the most important things, this event is organized by the Energy Storage Cluster, Chulalongkorn University, and National Science and Technology Development Agency. And the events are supported by the Office of National Higher Education, Science Research and Innovation Policy Council, and the Program Unit for Human Resource and Institutional Development Research and Innovation. Today, it's our great honor to have Professor Falko Mahlendorf with us. I'm going to share the session. Dr. Falko Mahlendorf studied chemistry at the University of Brunswick and Freiburg. In 1995, he obtained his PhD at the Albert Ludwig University in Freiburg, Germany, at the Faculty of Chemistry. Since 1989, he worked in the field of hydrogen and fuel cell technology at the Fraunhofer Institute Solar Energy Systems in Freiburg and at the Motoren Turbinen Union in München. Since 1996, he works as a senior scientist and lecturer at the Department of Energy Technology at the University of Duisburg-Essen, Germany. He is involved in a number of research projects in the fields of battery and fuel cell development. During the session, if you have any questions, please leave them in the chat box. Of course, if you have questions now, you can leave in the chat box. So our speaker will address them later after talk. Now it is the time that, we will let everyone enjoy the lecture by Dr. Falko. Thank you very much.
Thank you, Surathep, for the nice introduction. And we know each other already for several years. Surathep has been in Germany. So it's really a pleasure to share with all of you some research results in zinc-based batteries here at the University of Duisburg-Essen in Germany. So my talk is structured in two parts. Part A is zinc airflow batteries, and in the second part we switch to zinc polyodide redox flow battery. So Duisburg is located in the western part of Germany. It's rather close to Düsseldorf or Cologne, and it's only 40 kilometers to the Netherlands. So we are here in the Department of Energy Technology, and our research focuses on lithium-ion and zinc air batteries, also simulation of fuel cells and combined heat and power systems. In our department, we have around 20 scientists, most of them PhD students. So around 20 years ago, we have founded a spin-off. In English, it's called the Fuel Cell Research Center. And as the name says, the target is to develop fuel cells, hydrogen and battery technology. So we operate a joint lithium-ion battery lab. And we have around 100 full-time employees there. So battery research in our group is carried out for more than 13 years, and we have focused. We began with focusing on lithium-ion and later lithium-sulfur systems, and in 2012 we started research in zinc air batteries. Some of our projects are listed here. I will not read all of them. So our approach is to use zinc slurries for the zinc airflow batteries. And the advantage is they possess a high energy density, as you can see here on the picture on the right top. The slurry is in a tank, and the slurry is pumped with the help of a pump through the anodic compartment. We have a separator, and on the cathode side, we have an oxygen electrode. The spent zinc slurry can be regenerated externally. Some of these options are depicted here down. For example, the spent fuel, the spent electrolyte can be shipped to zinc recyclers or refiners. Or, of course, as depicted here on the bottom right, we have the option to feed it to an electrolysis unit and then electrochemically regenerate the fuel. So this approach has the advantage that we don't need a bifunctional electrode. We do not even need a 3-electrode setup. And as in any flow battery, the power is independent from the capacity. So here we see what our slurry looks like. It's the main ingredient is of course the zinc powder. We obtain the zinc powder here from a company in Duisburg also. It's Grillo Werke, they are called, and they are one of the leading zinc producers also for zinc, for primary zinc air batteries. The particles have a diameter of around 50 to 70 microns. In this SEM photo, they are perfectly spherically, but other forms can be produced, and we also tested them electrochemically. Our electrolyte is made up of the zinc powder, and it's an alkaline electrolyte. We mainly use 7 molar potassium hydroxide, and the electrolyte is stabilized with the help of a binder. Mainly we use PAA, polyacrylic acid, and we add some zinc oxide for the purpose of suppressing hydrogen evolution. And sometimes we add one or two additives to improve the performance. So these zinc slurries have a high energy density, and so this is depicted here on a per unit mass basis, on a per unit volume basis. On the x-axis, you'd see the zinc content. So this is just the weight percent of zinc. And when you look here, 70% zinc slurry has around 600 watt-hours per kilogram and almost 2,000 watt-hours per liter. So the point is how to make use of this high energy content in a zinc air battery. So when we look first to the reaction equation, zinc is converted to zincate when we discharge the battery, and once electrolyte cannot solve zincate anymore, zinc oxide precipitates. And I don't want to go into all of the details in this graph, but interesting is the blue line which goes horizontally at the bottom here, and this shows that only around 4.5 mole per liters of zincate can be dissolved, and even for this value you require some additives to stabilize the zincate in the solution. So with our zinc slurries with 50 or 70 weight percent zinc, there's so much zincate produced, we cannot keep it in solution. So inevitably, our zincate will precipitate as zinc oxide. And this is really our approach, what we've done here in our group. And I will show you that it is possible to operate slurry cells well above the zincate solubility limit. Flow cells, as I've just introduced to you, have this setup as depicted here. We have a current collector on the anode. Very often we use a copper current collector. Then we have the slurry anode, which is pumped through the cell, and you see all these 50 or 70 micrometer zinc particles. They are interconnected. They form a percolation network. And then we have here in yellow the separator, and in green the air electrode. I want to compare it first with a flow-assisted cell, which is a little bit similar, but has a solid zinc anode. We can see it here on the picture on the left in a charged state. So we have the current collector, the solid zinc electrode, then the electrolyte and the air electrode. And here in this, for flow-assisted cells, we need a lot of electrolyte, which is pumped through the cell to solve or to dissolve all the zincate that is produced. In the discharged state, all the solid zinc anode is gone, and all the zinc is in the electrolyte as zincate. So there's an advantage. We have a relatively high cycling stability with this kind of system, and but this operates, of course, below the zincate solubility limit. We have done some experiments to characterize and to compare these two ways of battery operation. Here we have in black line is the flow battery, so this has our slurry, and then in red we have the flow-assisted battery. And for both experiments, we have taken the same current density, 20 milliamps per square centimeter. The slurry cell had a 50 weight % slurry, and for the flow-assisted battery, we had dissolved 0.9 mole per liters of zinc oxide, and then converted it to zinc. So what is obvious here, the flow-assisted battery has quite a high depth of discharge, or DOD abbreviated, of 85%. And so the flow battery has a DOD of only 40%. And also the cell voltage levels are different. The flow-assisted battery has a lower operating voltage, but a long plateau until a large DOD is reached. So the characteristics are really a little bit different. And what is most striking, of course, that the capacity in amp hours is much higher for the flow battery. As I've said to you, we have 50 weight % of zinc in the slurry, and we have, of course, less zinc available for the flow-assisted battery experiment, which is only around 8 amp hours. So this is the advantage of using flow batteries with slurries. So flow-assisted batteries are easier to cycle. They have a stable discharge voltage, and flow batteries have a much higher energy density. Power and capacity are independent from each other, and they show a higher discharge voltage. I want to move on and show to you some of the cell concepts that we have developed for zinc alkaline fuel cell stacks. We started with taking classic fuel cell concepts and adapting them to the zinc air battery, and then we moved on to planar design concepts. So this is a depiction of a typical hydrogen fuel cell, PM, proton exchange membrane fuel cell. We see in the upper picture the bipolar plates, and then we have some sealing, the gas diffusion layer, the membrane electrode assembly, and again the bipolar plate. And these bipolar plates are made of a carbon compound material, which can be either hot pressed or injection molding. And in our institute, the Fuel Cell Research Center, we developed the injection molding process for these plates. So we started with adapting these plates to the purpose of our zinc air battery. In the upper picture, cathode flow field is depicted just like in PEM fuel cells. We have 4 identical channels that are, it's a serpentine flow field, very often used in PEM fuel cells. And in the bottom, you see a zinc slurry flow field with parallel channels. The channels vary a little bit in diameter. This might be not easy to see for you, to avoid uneven slurry speed distributions. And we tested and also simulated the flow distribution in the zinc side of the cell. On the bottom left, you see a simulation of the flow speed. This might be much too small to read the speeds here, but you see it's quite a stable slurry flow speed that results in even current distribution, and we did not detect any cell blockage. We also studied the flow behavior with the help of the technique PIV, which is particle image velocimetry. And this means here one part, the cathodic part of the cell is replaced just with a glass plate, and we pump a fluid, not our slurry, through the cell, and this fluid, into this fluid, we give seed particles, and with the help of these seed particles and laser flashes, the movement of these particles through the flow field can be recorded by a camera. So for several geometries, we use the PIV technique. Then we build a 3-cell stack with the help of these anodic and cathodic flow fields, and we did not see any leakage and also had a stable operation. And here's depicted how the zinc flows in the single cell mode. Here is the red line with slurry in and slurry out, and on the right photo you see the way the zinc flows through the 3-cell short stack. You can say it's a parallel slurry distribution. We also developed other flow field designs here for the anode. It's a serpentine flow field, and the zinc slurry enters through a round channel at the bottom, and then is split into 2 serpentines with semicircular cross section, and then it exits at the top right again through a round channel. So there are no changes of flow speed in the cell, no change of flow speed between the cell and the inlet and outlet tubes. And we see the current collector, which is made of copper. There is one disadvantage, or let's say 2 disadvantages of this serpentine design. We have an uneven distance between the current collector and the separator, which lies just above this flow field. And because of the serpentine structure, we have a relatively high pumping resistance. So here we see a current voltage curve. We can obtain high current densities up to several hundred milliamps per square centimeter, but due to the high pumping resistance, water from the electrolyte is forced through the separator, and it leads to cathode flooding, and the water, of course, that is on the cathode side is lacking on the anode side, and this leads to zinc deposits in the serpentine, as you can see here on the picture in the bottom left. So this led us to consider different designs. Here is a planar design, which is depicted here on the left photo. Again, we have a glass plate instead of the cathode side here to study the flow behavior. The zinc slurry is coming from the bottom side. It is just moving upwards, and we see that we have almost the same flow speed, or we have the same flow speed in the cell and the tubes, and the zinc flow is quite regularly and laminar, flowing over the current collector. We have studied it also with PIV measurements. Again, on the right top picture, you see results from the PIV measurements. If you would look, or if you could look at this picture in detail, you would see a lot of very small velocity vectors, and this is just the output from the PIV measurements. And it is also graphically displayed here in the bottom right, and you can see the different velocities as obtained from the PIV measurements. So we use this planar design to build a larger stack. We have here 160 square centimeter active area. The anodic side is displayed on the bottom right picture. It's almost symmetrically built up. We have here the current collector made out of copper, and on the bottom and on the top, we have the inlet and outlet of the zinc slurry. We have made it symmetrically to obtain an even flow speed distribution. This is important to avoid zinc sedimentation. And the picture above shows again the velocity distribution as obtained from PIV measurements. So we use this modular design to build up a 3-cell salt stack with a 480 square centimeter active area, and the peak power was a little bit more than 140 watt, which you can see here. The power axis is on the right side, and the green triangles show the power for the 3-cell measurement. So high current densities are possible also in the stacks of several hundred milliamps per square centimeter, and we did not observe a large difference between the single cell and the 3-cell stack performance. So these were the cell stacks, some of the cell stacks that we designed, and we also are doing some research on electrolytes. There are some problems of the classic potassium hydroxide electrolytes that are probably well known to you. One problem is the electrolyte decomposition, which leads to evolution of hydrogen. And so you probably know that zinc is kinetically stable in KOH, but not thermodynamically. So hydrogen evolution in acid media, in acid solutions is of course much more pronounced. But even in our alkaline electrolyte, we have some hydrogen evolution, and especially this is also temperature dependent. In summer, when we have higher temperatures in the lab, we have more gas evolution. And of course, carbonate formation is a well-known problem for the alkaline electrolyte. CO2 is taken up from the atmosphere, and then potassium carbonate forms and blocks the pores of the air electrode. So this was a motivation to look into ionic liquids. We had the chance to get a funded project. Ionic liquids are salts with melting points well below 100 degrees. They are made up of large ions, typical cations and anions are displayed here. But even more interesting are the so-called deep eutectic solvents. We have a mixture of a hydrogen bond donor and an acceptor. Most common acceptor is choline chloride, depicted here on the right side. And most common donors are ethylene, glycol, and urea. And we see here a diagram for where you see this eutectic point. So we tried, or here again, you see the different characteristics. Ionic liquids are, of course, expensive due to low production volume. Sometimes they have unknown toxicity, but they have a large electrochemical window of 4 to 5 volt, which is very favorable. DES have a somewhat smaller electrochemical window, but it's still big enough for our zinc air cell, which has open circuit voltage of 1.6, 1.7 volt. So, and DES chemicals are well known. Generally, they're non-toxic and also biodegradable. So what we did, we tried to increase the conductivity because the conductivity is too low to have good test results in the zinc air environment. So we took mixtures of for example, 1 part choline chloride with 2 parts ethylene glycol, abbreviated as 1,2-CE, or 1 part choline chloride with 2 parts urea, abbreviated as 1,2-CU. And you see it, the conductivity is displayed in millisiemens per centimeter over the water content. And for example, we get conductivities of 80 millisiemens per centimeter at 58% water content. So this is well above the value of 0.75 millisiemens per centimeter for pure 1,2-CU. So we were able to increase the conductivity even further with the help of some additives into the range of 160 millisiemens per centimeter. This is still lower than the conductivity of 7 molar potassium hydroxide, which is depicted here in the above graph. The conductivity is around 500 millisiemens per centimeter. So we did some performance tests And we found out, or what did we test? We tested here, for example, 48% mixture of 1 part choline chloride and 2 parts urea. So this is 40%, the rest is around 60% water. And then we have a 60% of the 1,2-Cu, and this has, of course, 40% water. And some selected additives we added up to 2 moles per liter. And the additives really can improve the performance. We have a typical current voltage curves here. We have current densities up to around 60 milliamps per square centimeter. But of course, interesting is the operation point around 1 volt. So at around 1 volt, we have a current density of 40 milliamps per square centimeter. And our project goal was to achieve around 50 milliamps per square centimeter. So we did not reach it exactly, but we're quite close to it, especially when you consider that in the literature on ionic liquids and epoelectric solvent electrolytes, generally current densities in the range of 0.5 milliamps per square centimeter are reported. So we will continue these experiments also with new DES components and also studying some more additives. So I want to give a short outlook for the slurry-based zinc batteries. The operation of zinc air batteries with slurry electrodes beyond the zincate solubility limit has been shown by us, but also by other groups. But achieving high current densities and high depths of discharge under these conditions remains very challenging. So one approach that we will take within a funded project soon is operation of zinc air batteries with coated zinc particles. This coating has to be electrically conductive but permeable for hydroxide ions, of course. The hydroxide ions have to be fused through the coating and then react with the zinc to yield zincate. Like this, the zincate, which is produced during discharge, largely remains locally inside the coated structure, and then it can be, or it will be, electrochemically reduced again to zinc. We have a university partner who has already some experience in applying these electrically conductive, you can say glass-like coatings. Generally, zinc air batteries, of course, have a small disadvantage that they have a large voltage gap between oxygen evolution and oxygen reduction. So this will always lower the voltage efficiency, so the overall efficiency is maybe 40, 45 or 50%. So one possibility is, of course, to get rid of the oxygen electrode and replace it with a different chemistry. So we have a new project which has just started, and the aim is to develop a nickel-zinc double flow battery. So we will have slurries flowing on both sides, on the anode side and on the cathode side. And the slurries are based on zinc. This is our zinc slurry, and nickel oxyhydroxide. This combines in principle the positive properties of solid nickel zinc batteries with the advantages of a flow battery. But of course, you can imagine this is also quite challenging to develop a double flow battery based on these slurries. So let's move on to another topic, part B of my talk, and this is the zinc polyiodide redox flow battery. This is a very interesting battery chemistry, and zinc polyiodide redox flow battery has been mentioned in the literature. I think it was around 5 or maybe 6 years ago when the first reports came up. So this is a relatively new battery. And of course, we have zinc. Zinc on the anode side during discharge is oxidized, as it's well known, to give zinc ions. But on the cathode side, this time we have triiodide, negatively charged triiodide. This takes up the electrons to yield 3 ions of iodide. So the overall reaction is then depicted here. Zinc plus triiodide gives zinc ions and 3 ions of iodide. We have OCV, open circuit voltage, of around 1.3 volt. And the setup of the cell is depicted schematically here. We have, maybe you can say, just like in all vanadium redox flow batteries, we have these graphite felts which serve as electrodes on both sides, on the anode side and the cathode sides. And then we have here the electrolyte compartment. The electrolyte is pumped on each side. And so both compartments are separated by a cation exchange membrane. And only the zinc ions can, in an ideal sense, can move through this membrane. So they transport the current. Zinc and iodine are non-hazardous, and especially zinc is quite cheap. Iodine is a little bit more expensive, but less expensive than the vanadium, for example. And this battery chemistry allows for a high volumetric energy density. As you can see here, we start generally by using zinc iodide, and zinc iodide is soluble up to 5 mole per liter. So you can compare this value with around 1.6, 1.7 mole per liter of vanadium, of vanadium salts that can be dissolved in acid. We have a 2 electron transfer. In the case of vanadium, we have a 1 electron transfer. And the electrolyte volume at the anode side can be kept very small. So we see here again in the bottom right picture the cell, and you see that the tank for the electrolyte on the anode side is drawn much smaller. So this is to visualize that the electrolyte volume at the anode side can in principle be kept much smaller. And as I've said, only the zinc ions diffuse through the membrane and they act as a charge carrier. So in theory, but really only in theory, we can expect almost 10 times higher volumetric energy density in comparison to the all vanadium flow battery. This is shown also in the graph on the left side, where we have on the y-axis the volumetric energy density in watt-hours per liter. Here, starting with the vanadium flow battery, then zinc bromine, zinc polyiodide has been demonstrated, and zinc polyiodide in a theoretical calculation. In theory, we could reach up to 350 watt-hours per liter, and this is really quite a lot. Then we are in the league of lithium-ion batteries almost. So that's a good motivation for doing research in this kind of battery. So the electrolyte is composed of zinc iodide, and when you try to solve zinc iodide, this leads to colorless precipitates. Zinc oxide is formed a little bit, which can be seen here on the right side. So you need an additive to dissolve the zinc oxide properly. And one of these additives is ammonium chloride. It complexes the zinc ions in different complexes and really improves the cycling behavior. We see it here in the it's a graph on the left side. We have on the left axis a capacity in amp-hours per liter, and then we see here the cycles, up to 45 cycles, as a function of the amount of ammonium chloride. And once we add 1 or 2 moles of ammonium chloride, we can obtain 40-45 cycles. It is interesting to note that in the triiodide ion, iodine, here in yellow you see the iodine molecule, is stabilized, and this really wastes one ion of iodide. So if we take, for example, zinc bromide, then iodine can be stabilized as I2Br minus. The molecule is here depicted in the middle. And this really, and like this, we can really unlock the full capacity, which is shown here qualitatively on the picture on the right top, when we can complex the ion with the bromine, then we can really oxidize and reduce all of the iodine. So our electrolyte then is composed, for example, of zinc iodide, of zinc bromide, and of ammonium chloride. Like this, the capacity, or you can say the energy density, is increased, which is shown here in the voltage capacity curve on the left. We have here the red line, on the red discharge curve, for example, where we have a capacity of 12 amp hours per liter upon adding zinc bromide, and without zinc bromide we have here around 9 amp hours per liter. So this has been reported in the literature, and the depth of discharge is of course important with respect to how many cycles can be obtained. This is depicted here in the right curve. We have the capacity again on the left y-axis in amp hour per liters, and again we have here the cycles and the coulombic efficiency. So when we charge in this, when we try to charge and discharge 100% our battery, then we can only perform a few cycles. But once we go down a little bit with the depth of discharge, maybe to 75%, we can obtain again around 50 cycles, which is of course not enough yet for a good battery. So the question for us is which side, the anode or the cathode side, is really limiting the performance at the moment. So we devised some half-cell experiments. I will show you here one experiment for the polyiodide side. We use a zinc foam as anode material, and this acts as a zinc reservoir and that can be dissolved during discharging instead of the zinc deposit from the charging. So we see here, like this, we can eliminate the zinc half cell, so to say, and only concentrate on the polyiodide side. And we have here around 140 cycles recorded for several times with a high reversibility. So we think that the polyiodide reaction is highly reversible. It can maybe be accelerated with the help of a catalyst, but this is quite stable. And we think that reversibility is not so good on the zinc side. So this is where we focus on at the moment. What we've done next is constructing a 100 square centimeter flow cell with graphite felts as the catalyst, so to say, as the electrodes and catalysts, flow frames made of PTFE, and the cation exchange membrane from lithium. We designed also 3 different flow fields. The simplest one is a flow-through design, and then we have interdigitated designs and serpentine flow fields, which is here depicted in the table. I cannot go to all the details now. We did some simulations on the flow velocity distribution for the 3 flow field designs. We did measurements of the ohmic resistance with the help of impedance spectroscopy. And you can see here qualitatively in the 3 simulation diagrams the flow velocity distribution. So then we recorded current voltage curves for these three flow fields in the 100 square centimeter cell. And we varied the felt compression. So this is the electrode compression here in the left graph, it's 11%, in the right graph, it's 33%. But regardless of the felt compression, always the flow field, so relatively simple flows through design yielded the best performance. So we have, for this concentration here, we have current densities of several hundred milliamps per square centimeter. And this is really so far the highest literature reported current densities for this kind of battery. We did some cycling, charging with almost 50 milliamps per square centimeter, and discharging was a little bit reduced, with half the current density. For the three flow field designs here, flows through, interdigitated, and serpentine. And the best results, this is more than 60 cycles could be obtained for the flow through design of the flow field at the anode. Then we raised the concentration of the zinc iodide. In all of the experiments that you've seen so far, we only used 0.5 moles zinc iodide. Now we used here 2.5 moles of zinc iodide plus ammonium bromide, ammonium for the zinc complexation and bromide for the iodine complexation, and this can be combined in one compound. So with a higher concentration of zinc iodide, even higher currents can be obtained. They are more than 500 milliamps per square centimeter, and again, for the flow-through design, we yield the best performing cell. We did some cycle experiments, charge-discharge cycles with a high concentration. And as you can see here, again, we could obtain more than 50 cycles, but the coulombic efficiency is lower than compared to the experiments with a lower concentration. So there's still really some room for improvement. As I've pointed out before, we can still, in principle, increase the concentration up to 5 moles per liter. We can exploit bromide to complex iodine and reduce the anolyte volume to achieve higher energy densities. So in summary, this zinc polyiodine redox battery is really interesting because of the high volumetric energy density. We tested here 3 different flow field types, and interestingly, the simplest flow field, the flow-through design, gave the best results. We obtained quite high current densities, so which makes it in principle attractive. The goal, from my point of view, would be a flow battery that can operate with a current density of around 200 milliamps per square centimeter. But of course, the reversibility, and we think especially on the zinc side, has to be optimized. So this is really the point where we do a lot of experiments right now. And of course, a little bit larger stack is under construction. We build a stack based on an active area with 250 square centimeter, and we will show a 5 or 10 cell stack of this side. So with this, I want to close my presentation and thank everyone for your attention. And if you have some questions, don't hesitate to ask.
Thank you. Thank you very much. So do we have questions from the audience? Okay, we are waiting for a question from the audience. But at the time, while I would like to ask you about the shunt current. So for slowly feeding, I mean, well, compare with the hybrid flow battery where zinc solid deposit inside and we feed just only electrolyte. And slowly type, do you have problem with shunt current?
With chunk currents for the slurry type, yeah, in principle, shunt currents should be a big problem. So with the three cell stacks that we have built so far, we operated them in a parallel fashion, where the slurry does not flow through all of the cells. We have also tried this, but then it's true, we run into the problem of shunt currents. So this is a problem of the high zinc concentration of 50 or maybe 70% in this slurry. No?
I see.
Yes, you're right.
Okay. And you mentioned that, well, your new project on zinc nickel, well, nickel oxide, right? Nickel oxyhydroxide. So we did same, right? You make it as a slurry, right?
Yeah. Yes. So our because I say the standard nickel zinc battery is well known and has good performance also, and we want to try to do our slurry approach also to the nickel side of the battery. You know?
I see.
But of course, the nickel, there's one problem, of course, the nickel or the nickel oxide is not conductive, it's not zinc.
Right.
So we need a conductive coating on the particles, and this is one part of the experimental program.
I see. Yeah, it's possible because you just change nickel oxide to nickel oxyhydroxide, which both are solid. So
Yes.
well, you don't have to change.
And non-conductive.
Right. Just coating that. Yeah, but
yeah,
for zinc you cannot do that because zinc dissolve, right? So we lost that particle already. I see.
Yeah, and zinc shows quite a large volume change.
Yeah, right.
So in the one project that I told you about in the summary, we also want to coat the zinc particles with a kind of it's glass-like coating, which is also quite stable. So the zinc oxide the zincate that is forming basically stays inside this coating and can then electrochemically be reduced again up on charging the battery. Okay. This is the approach. But of course, there are some issues with the stability of this glass-like coating in strong alkaline media. So maybe we will change the electrolyte a little bit in this project also.
I see. Okay. And I also have one question regarding zinc polyiodide. Zinc polyiodide is very interesting. Of course, we test that in our lab, but not slurry type. We use the hybrid flow where zinc is deposit on the carbon felt or nickel foam, something like that. Well, we think that the big problem is the crossover of iodine.
Oh.
Do you have
did you also use a cation exchange membrane?
Yes, with Navia.
And you still observe the crossover, yeah?
Yeah, for a long time.
We also, yes, you're right. There is some crossover, and this depends on the concentration of the iodide. We did some titration of the iodine crossover concentration. No? I could not present all of these things here in the amount of time, but you are right. So when you take a very small, let's say there are membranes of 30 microns, so the crossover becomes more important. When you take a thicker membrane, the crossover becomes less. but of course the ohmic resistance of the membrane is increasing.
I see.
So there has to be a compromise always.
I see. So wow, because one of
with the small membranes, with the very thin membranes, you can achieve very high current densities.
yeah,
But maybe this is not suitable for long-term operation, for long-term cycling, because of the crossover that you mentioned.
yeah, right. Wow.
Mm.
And any more question from the floor, from the audience? Oh yeah, we have question from the audience. Can you explain about some separators? What are best separator for seeing zip in your mind? Zip. Well, could you? Well, the audience, Mr. Adnan, could you please tell us the abbreviation of zip? You mean zinc ion battery or zinc iodine battery? I suppose it's zinc polyiodine battery. Yeah.
Yeah. Okay. In that case, we've just have been talking a little bit about this point. We do not use a separator. We do use a cation ion exchange membrane. It's a Nafion membrane, which is also used in a similar way in PEM fuel cells. So there are a lot of different membranes available with different thicknesses. So this is only our expertise. You cannot use a simple separator, but you need a really cation membrane, so that in principle, in theory, only the zinc ion can diffuse through this membrane. But of course, we have some crossover, as we were just been talking about.
Okay. Yeah, we have another question from my colleague, from Miss Rong, from Dr. Rong, but but because it's too long, so I invite her on stage. So could you accept our invitation and well ask question by yourself? Okay, we skip your okay, you're coming to stage. Your microphone is muted, so well unmute your microphone and ask question directly. Hi, can you say something, Dr. Rong?
Yeah, it's
maybe she have problem.
It's a question on the flow fields. Yeah.
All right. Okay, I read her question. I have some questions regarding flow field. Right. For someone who is trying out new system, would you recommend trying on the flow through or typical serpentine? Serpentine, right? Also, for the flow through flow field, is there any limitation to how large, how small the active area that this flow field type would work better than others? Okay.
Yeah, let's say the first part, for us, it also was a little bit surprising that quite simple flow-through design has resulted in the best performance. So because let's say there's a lot of literature on using different flow fields coming from the all-vanadium redox flow battery. So we also read this literature and then made our design. So for the serpentine flow fields, we have devised several serpentines with different channel widths and several serpentines flowing parallel, where the flow is parallel through a serpentine flow field. So there are a lot of different possibilities. It's not easy really to give you a recommendation which is the best flow field, but you should have, at least consider all the available literature from the all-vanadium redox battery. And with respect to the limitations with the active area, that is not easy to answer for me right now. I don't know. This is kind of limitation. But flow field or not flow field is a big issue always, and we we have another project in the field of vanadium redox batteries, where we set up a segmented cell, and we also realize different flow fields in this segmented setup. So, and then I think we will soon get more detailed results on what is really the best performing flow field design. But and later on we also want to use this segmented cell for the zinc polyodiene fuel cell.
All right, we have another question from Mr. Wanchai. Right. Regarding the design of the flow cell, I find importance of one cell component, which is the pump. Yeah, right. For me, it makes the cell design exceptional and be more complicated. Moreover, the pump needs some energy to function. Does this require energy offset from the reported cell performance?
Yes. So I think this is the case for any type of flow battery. For example, in the all vanadium redox flow batteries, you have two pumps, one for the anode side and one for the cathode side. And of course, they need some energy. This is a parasitic energy. So then we come back to the flow fields. The aim is to design a good performing flow field, which requires with a low pressure loss. Low pressure loss translate into low pumping energy. Now, this is the motivation actually.
Yeah. Right. Well, no matter what type of battery system, you have to take these things into account, no matter the heat.
Yes.
In some system, you have to keep the system at elevated temperature. So you have to consider that into your economic analysis. All right. The next question is, could you explain reason of using binder for slurry type battery and zinc particle utilization in the slurry?
Yeah, that's a good question. So when you want to make a slurry without binder, the slurry is not stable. The zinc particles, or depending on the zinc particle size, they will just sediment. So you, in order to have a good slurry, you need a few percent of a binder like PAA. This is already well documented in the literature, let's say 20, 30 years ago. And we also tried to use different binders, and all of them work, but you need a few percent, otherwise you have sedimentation. And the zinc particle utilization, sorry, that's also a good question. We have done a lot of experiments on this part, and a PhD student is also working on this. So zinc particle utilization, so this is a DOD, the depth of discharge in the end, depends very much on the current density. If you try to discharge the zinc particles with a high current density, this so-called type 2 zinc oxide is forming and is blocking everything. So when you discharge with lower current densities, you get much higher DODs, and also adding some additives can have a good effect on the DOD. Yeah, but this is a broad field of research.
Okay, we have one more question by Dr. Gopal. Is there any impact to reduce size zinc slurry, millimeter to nanometer? And the second question is, why I3? Why triiodide? What about other halogen like chlorine, bromine? Is there any specific reason? Okay.
Yeah, so first, it is possible to reduce the size of the individual particles. We received them from the company Grillo, and they were also project partners. And within these projects, the thing size and shape was varied, but not to the nanometer scale. I think nobody wants to deal with nanometer sized powders. This is really like dust and is not really good for the health. So we want to keep the size in the millimeter, in the micrometer range, not necessarily in the nanometer range and not necessarily in the millimeter range. And of course, when you want to charge the cell, then all these shapes of the zinc particles, they will anyway change very much when you charge them electrically. After the first charge, you don't have such a nice sphere or any other shape that you were using. And the second question is about the other halogens. That might be possible, but we were just building our research on the research papers that we found in the literature on the zinc polyiodide on battery, and yeah, try to combine these results with our experience in building stacks.
Okay, and I can add some of my comments on this point, because well, for if you size, you go down from millimeter to nanometer, of course you have higher surface and you have problem with corrosion and parasitic reactions, of course, right? Yeah, just that my comment. Now,
Yeah,
we can go
right.
on to the second question. Why iodine, triiodide? What about other halogen like chlorine, bromine? Is there any specific reason?
Well, I'm not sure. This is these research reports were on iodine, and because iodine in the end is a solid and chlorine is a gas,
Yes.
so I don't think you can use it in that way.
Mm-hmm. Yeah.
Maybe you have some ideas on that.
Yeah, the idea, if you search a literature a long time ago, well, chlorine also have been used, right? But it's very difficult to handle because it's gas phase. You need a
And dangerous.
it is dangerous, of course. Even bromine, of course, is already commercialized zinc bromine system, right?
Yeah.
Yeah.
Yes.
But of
Right.
course, at elevated temperature, while you have problem of evaporation of a bromine, and if it's built up in the closed space, I mean in the room, you have problem. It's toxic, right?
Yeah.
Mm-hmm.
Yes, definitely.
Okay, we have more questions. Could you please give us about the real application of this cell? Since we have to feed the slurry, which is the fuel in this case, so the cell should be stationed. Oh, just one moment. So the cell should be stationed in some place and will not be applicable for moving vehicle, because we will need to install a pump on our car. This might be a major drawback of the flow cell. Could you comment on this?
Yes, I think the question is referring to the zinc slurry cells. Of course, this kind of battery is not designed for mobile applications. 40 years ago, there were development efforts from Appleby and co-workers in France who really set out to develop this kind of slurry-based battery for mobile applications. But I don't think this is not realistic. We are looking at rather large stationary batteries where you can have a big fuel tank and couple it with fluctuating solar or wind energy, something like this.
Okay. Any more questions from the audience? Well, I have one more question about the status from in Germany, because we learned from the news that, well, in 2020 we produce a lot of electricity from renewable energy, especially from solar PV, solar panel, and also from wind. But the problem is we cannot store it because the energy storage for that size, for that application was limited. So we lost those things. Those electricity, clean energy, right? Clean electricity produced. What about the situation in Germany now?
Yeah, that's. I think in every country this is a problem. Once you have a large share of renewable energy, you run into the problem of storing at least some part of the produced electricity. And of course, you can, for example, do it in big stationary batteries. There are projects with lithium-ion batteries, or this is why we have these funded projects in Germany, also with other battery types, to have in the end big stationary batteries, or other researchers who favor hydrogen. They say we must store this renewable energy by electrolysis in hydrogen, and once you lead the energy again, you put the hydrogen again into a fuel cell and then get the electricity out again. So I think these are the main options to store to store this kind of energy.
Okay, so we can expect a huge market, huge and growing market for stationary energy storage.
I think so.
Any more questions from the audience? If not, I'm going to close the session. And of course, because we already record the video, I would like to ask your permission to distribute the recorded video to the public.
Yeah, you can do so. That's no problem from my side.
Yeah, thank you very much. So, well, thank you for joining us today. Yeah, and I hope that you have a good time, even that the situation is still, well, I hope it's getting better. All right.
Yeah, I hope you can come to Germany or Europe again, and then we can meet and discuss some projects.
Sure. Thank you very much. Yeah, once the border is open again, and then we will have a
yes.
Okay. Thank you very much.
Thank you.
Have a good day. Bye.
Okay, thank you. Bye.